Hello, friends. This is Jim here with Science Talk, and I want to discuss with you an interesting article I came across, and I thought I'd share it with you. And as you can see right there from the headline, Earth may have been a water world 3 billion years ago. Now, it's still a water world because more than 70% of the surface is covered by water. In fact, I have long held the thought that this planet should be called Oceanus. Be that as it may. So we're looking here at a nice picture of the southern hemisphere. You can see Australia there, the Antarctica poking out there, and big expanses of the Pacific here and the Southern Ocean, etc. So why this photo here? Because of a remarkable find in northwestern Australia. Okay, so let's go through here. Scientists have found evidence that Earth was covered by a global ocean that turned the planet into a water world more than 3 billion years ago. Telltale chemical signatures were spotted in an ancient chunk of ocean crust, which point to a planet once devoid of continents, which are the largest land masses on Earth. Now, not to say it was one big water ball, but there might have been, like a Madagascar or a New Zealand or a Novaya Zemlya poking through. But having large continents, the evidence is, and the conclusion that the scientists are drawing is that no, that was not such. So if findings are confirmed by future work, how science works, you get some information, then you look for evidence to continue to support it or refute it. This will help researchers refine their theories on where and how the first single-celled life emerged on Earth and what this may be for exoplanet, life on exoplanet possibilities. So there's a paper that appeared in this Nature Geoscience, and the scientists wrote that the early Earth without emergent continents may have resembled a water world, providing an important environmental constraint on the origin and evolution of life on Earth, as well as its possible existence elsewhere. So Boswell Wing of the University of Colorado Boulder and his former postdoctoral student Benjamin Johnson, and Johnson's now Iowa State University. They did this project to examine this very question. Their work was at a site called the Panorama District in northwestern Australia's outback, where a 3.2 billion year old slab of ocean floor has been turned on its side. Locked inside the ancient crust are chemical clues about the seawater that covered Earth at the time. Now, before we go any further, finding oceanic crust 3.2 billion years old is extremely rare because we have the plate tectonics where plates meet and you have a subduction zone. A lot of the oceanic crust goes down the subduction zone into the mantle. And the rock literally melts and it emerges, after many years out the oceanic ridges where it emerges. So finding oceanic crust of that age is extremely rare find. Now, the scientists focused on different types of oxygen that seawater carried into the crust. In particular, the relative amounts of two isotopes, oxygen-16 and this ever so slightly heavier oxygen-18. Now, there's also an oxygen-17, but that's even rarer. But the two main isotopes of oxygen are 16 and 18. And basically what this means is that oxygen will always have 8 protons in the nucleus. That the number of protons, the atomic number, is what identifies the element. But what differs is the number of neutrons. So O16 has 8 protons, 8 neutrons. O18 has 8 protons and 10 neutrons. So you basically change the number of neutrons, you get different isotopes. Now, I did a very lengthy video on isotopic fractionation, where I explain O18, O16 fractionation, C13, C12, C14, C12 fractionation, N15, N14 to a lesser degree. I explain all that in terms of ice sheets, whether or not there was deep water formation or the thermohaline vertical current. I did a very lengthy video on that. If you have not already seen that, I would suggest that you please check that out, because the information there will most likely help with what's being presented in this video segment. So what did they find? They found that seawater contained more oxygen 18 when the crust was formed 3.2 billion years ago. Seawater contained more oxygen 18 than in the crust. The most likely explanation, they think, that Earth had no continents at the time, because when continents form, and this is the key point, the clays they contain, that is, the clays that, which are minerals that help start forming the land masses, the clays they absorb the heavier oxygen isotopes. So in other words, you're going to, as the land masses form, they're going to absorb the O18 from the ocean, incorporated into the minerals that now form the land masses. That is what that is saying. Dr. Johnson says, without continents above the ocean, the oxygen value would be distinct from today, which is exactly what was found. And it's different in a way that is most easily explained without land to get rained on without soil formation. Now, as I said at the outset, does not mean Earth was entirely landless. It's just that you might have what they call small microcontinents, may have poked out of the ocean here or there and that kind of stuff. Also, water levels were probably higher. Now, the researchers do explore other possible explanations that the same chemical signature could arise if continents formed far slower in the deep path than they do today, or if the continental clays that absorb heavy oxygen isotopes formed in the sea rather than on land. So those are possibilities that need to be considered. This is where further research is going to try and ascertain, to look into those very questions. Not quite sure when continents first formed, most likely through the gradual slowing of heat loss in the Earth's interior. Earth's interior, radioactive decay, heat loss, that's what they're referring to. About 500 million years ago, okay, that's 500 million years ago, that's 500 million years, Earth was dominated by the supercontinent Gondwana, which lasted into the Jurassic period, about 180 million years ago. And now Dr. Wing is going to look at oxygen isotope ratios in younger oceanic crust in the hopes of nailing down when the global continents emerge. Now, to get those samples, you go right down to the ocean floor and drill and pull up some sediment cores. The oldest preserved continental material is approximately 4 billion years old, and subsequent growth and emergence of the continental land masses is constantly debated. And this is a statement from Dr. Alan Hastie, who is an igneous petrologist at the University of Birmingham. So basically says, Earth scientists use a variety of methods to try to estimate how the volume of the continents has changed over time. This is important as the volcanism associated with continental growth and erosion of land masses has modified the composition of Earth's ocean and atmosphere. Therefore, any new study to help us constrain the amount of continental emergence is welcome. So, what's the significance of this? Well, first of all, it helps us understand better the processes of planet Earth. How does planet form? Some of the physical processes involved. It tells us a lot about planet building up, the planet tearing down, and as stated at the outset, this could help us identify when life forms first emerged and in what capacity. What was the conditions that allowed life to emerge. Now, also keep in mind here, and this is not mentioned in the article, and I think it's important to mention, the amount of oxygen available way back then, 3 billion years ago, is probably going to be on the low side. Now, the planet is about 4.5 billion years old, and there's pretty good evidence that 3.5 billion to 4 billion years ago, we had the first single cell organism showing up, some bacteria. Not all the bacteria were photosynthesizers. Some of them use other chemical pathways to engage in primary productivity. The point is that the amount of oxygen, at least in the atmosphere, was going to be considerably less. So now, what is the source of the available oxygen? Might be some metabolic byproducts. It's going to be from water itself, H2O, right? It's going to be from silicates, from other clay materials and other geological entities that contain oxygen as part of the chemical structure. Those are going to be your main sources of oxygen. It wasn't until we started seeing more and more primary producers, single cell, multicellular plant, that started pumping out oxygen in greater amounts into the atmosphere where it built up. And of course, keep in mind, when oxygen was first being produced, it was a poison to a lot of organisms. And then organisms evolved where they can then say, we can utilize the oxygen for respiration. Be it as it may. So you want to keep that in mind, that the oxygen levels back then were not what they are today, especially in the atmosphere. What they were in the ocean, we can get a hint by looking at the fractionation. So it's just an interesting little topic I wanted to share with you guys. Kind of a bit of a break from the all the other stuff that's been going on. And so hope you found this interesting. And as I said before, if you really want to get a good handle on what isotopic fractionation is all about, which is in essence the methodology these guys engaged in, please check out my isotopic fractionation video. Thank you for your time. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.